In this PowerPoint video, we will discuss significant figures. A measurement contains numbers known with great certainty, except for the last digit, which has some uncertainty in it. It all depends on the measuring device. So if we look at our ruler up here, we have two rulers. Let's look at the top ruler. It's in centimeters. And a measuring device depends on the number of, the precision of the measuring device depends on the number of division markings. In the top ruler, we can see that the division markings are to the 1 centimeter. Now there's space between one division marking and another division marking, and your eyes can subdivide that into smaller division markings, and we can do that with any measuring device. So the top measuring ruler here can be measured to the tenths place, because the smallest division markings to the 1, we could read to the tenths. So here, for measuring our black block, we can see for certain it's 10 centimeters. And then we can subdivide this region and say it's about 0.2 centimeters. Now, some people might say it's 10.3, some people might say it's 10.1. We're all correct. That last number has a little bit of uncertainty in it. So we'll call this, using the top measuring device, it's 10.2 centimeters. Now, if we use the bottom ruler, this ruler here has division markings to the tenths place. So we can read this ruler to the hundredths place. So we can read the bottom ruler to great certainty, this black block, to 10.1. And it's about halfway in between, so I'm going to call that 10.15 centimeters. So the bottom measuring ruler has greater precision in measuring the black block than the top ruler. And we show that by, we can read this one to 2 decimal places, where the top ruler is only good to 1 decimal place. When we look at significant figures in a measurement, they can contain all the digits that are certain, and the last one has some uncertainty in it. Now, in any measured device, all non-zero numbers are significant. So if we have here, I forget to get a pen. Let's get a pen here. So if we have all non-zero digits, so if we have a measurement that's 124 centimeters, that's 124 is 3 significant figures. Okay, and I'm going to abbreviate significant figures just as SF in the future, but I wrote Sig Figs, so you know what that means. And as we go on, some measurements have zeros in it, and these depend on several factors. So if the zero is what we called captured, here if we have a measurement, for example, of 101 seconds, okay, 101 seconds, that zero is between 2 non-zero numbers. And so this measurement has actually 3 sig figs in it. Okay? That's a captured zero. Now, if we have leading zeros, like, for example, 0.0032 millimeters, for example, here, this is showing these zeros here are leading zeros, and, and they're basically just showing me where that decimal point is located. It's a placeholder. So these zeros here are not significant. So this measurement only has 2 sig figs in it. Now if we have trailing zeros, it's a little different. So if we have a zero after a non-zero number, like 32.0 liters, that zero here is after a non-zero number and after a decimal point. It is significant. So this measurement has 3 sig figs in it. If we have, for example, 10, where this zero is after a non-zero number and before a decimal point, and the decimal point is shown, that zero is significant. So this is 2 sig figs. If we have a measurement that has no decimal point, those trailing zeros could or could not be, may or may not be significant. So 800 might have 1, 2, or 3 sig figs. And to better let the reader know how many values in that measurement are significant, we should put it in scientific notation. So if it's 2 sig figs, we put 8.0 because this coefficient only shows significant numbers in the measurement times 10 to the second. If it's 1 sig fig, we just show 8. If all three are significant, then we would put 8.00 times 10 to the second.